All right, welcome back. We're going to talk now about matching a slope field to a differential equation. And so the slope field represents all of the particular solutions to a differential equation, and the solution would represent the antiderivative of a differential equation. And so when I look at the actual shapes of these curves, it will look like the antiderivatives. And so you can think about this, especially if you look at the differential equations we have over here, they're all in terms of x, which means it should be very easy for us to figure out what y is just by taking the antiderivative. If there were x's and y's, then we probably don't want to have to find the antiderivatives. We'd have to use separation of variables like we did in our last section in order to figure that out. So in these cases, we can just go ahead and integrate both sides. So if my derivative of y is sine of x, then I know that my y would have to be the antiderivative of sine, which is negative cosine x plus a constant. And so then I can look over at these graphs and figure out which one would look like negative cosine. Let's wait on that though. We're going to go ahead and find our other antiderivatives and then we'll worry about the matching. Okay, in number 2, we have 2x plus 4. So if we integrate both sides there, we have y equals, that would be x squared plus 4x plus a constant. Number 3, we've got the antiderivative of e to the x, which would just be e to the x plus c, super easy. Number 4, our antiderivative of 2 would be 2x plus a constant. Number 5, we'd have y equals x to the 4th over 4 minus 3x squared over 2 plus a constant. Number 6, the antiderivative of 2 cosine x would be 2 sine x plus a constant. Number 7, we'd have 4x minus x squared plus a constant. Number 8, we'd have x squared over 2 plus a constant. Number 9, we'd have x cubed over 3 plus a constant. And for number 10, oh, this is the tricky one. Don't forget the antiderivative of 1 over x is natural log of absolute value of x. So this is negative natural log absolute value of x plus c. Alrighty, so now let's do the matching. So you can do which ones are easiest first or just go down the line. I'm just going to go down the line. Negative cosine x plus c. So if I think about what cosine x looks like, that's what it looks like. So if it's negative, it's going to be reflected over the x-axis. So I'm looking for a shape like that. I've seen a couple different shapes, maybe D, maybe H, maybe I. And so what I want to keep in mind though is that I know that I would have a slope of 0 along the y-axis. And so I'm looking for one of these that has a slope of 0, and it's going to be I. So I can see if I fill in the graph here, kind of what I'm looking for, this graph of cosine flipped over. So that's I. I'm going to cross that off since we used it. I don't know what's happening with my board. Okay, number 2, x squared plus 4x plus c. I know that's going to be a parabola facing up. And I know it's not going to be symmetric to the y-axis just because it's shifted over because of that 4x. So I'm looking for some parabola facing up, shifted over. That's going to be A right here. Let's go ahead and actually fill in some of our graphs so we can kind of see their shapes over here. That will help us match up our solution curves. Now you can just pick any one you want. It doesn't have to be perfect here. And this is just helping us match up again, so it doesn't have to be really nice and perfect. We're just sketching it out. Okay, number 3, e to the x plus c. So remember, e to the x looks like that exponential growth. And so I can see that one is going to be B. Oh, I forgot to actually mark down number 2 was A. Well, apparently I'm having a little issue with my pen. Doesn't want to write where I write. It'll be okay. All right, 2x plus c, that's linear. So I'm looking for one of these graphs that's a line. That looks like J. Number 5, x to the 4th over 4 minus 3x squared plus c. So it's even degree, so I know it's going to be the same end behavior and positive leading coefficient, so it's going to be up and up. And then because it's to the 4th degree, I'm assuming I can see some shapes like that. So down, up, that kind of thing. So that looks like H. Sine of x for number 6. Looking for a sine curve. That's going to be D. So notice again, I don't have a slope of 0 here. I have like a slope of 1 along the y-axis. And then I have my first horizontal tangent probably at about pi over 2. So that is at D. Number 7, we have 4x minus x squared plus c. That's a parabola facing down. So looking for a parabola facing down and shift it over a little bit, that's going to be G. X squared over 2 plus c, that's a parabola facing up. Also, because there's no just single x term, I know that's going to be just the parent function shifted up, maybe stretched a little bit. And so that's symmetric to the y-axis. So that looks like F, this one right here. Number 9, x cubed over 3 plus c. So I'm looking for that x cubed S kind of shape. That one's C right here. And the last one, negative natural log absolute value of x plus c. Well, you can use process of elimination. It's E. But remember that natural log of x is kind of e to the x. It's flipped over. And so natural log of x, absolute value of x would just be that flipped over the y-axis as well. And then because of the negative, you can see over here that it's actually flipped over the x-axis. So that would give us that. All right, so that's how we do those if you are trying to match up with your differential equation. You might need to find your antiderivative. We'll do some examples later where you don't want to use your antiderivative. Let's match them up with some solution curves now. And so here the hard work is already done for us. We already have the solution curve. So we're literally matching it up to what the graphs look like. So let's again fill in our graphs. Again, this doesn't have to be perfect. Just trying to get your shapes here. Ooh, that one was really bad. I'll redo it. A little bit better. All right, so what I'd like you to do now is pause the video, try to see if you can match these up on your own, and then come back and check. Okay, welcome back. So we've got y equals x. That graph will look just like C right here. It's linear, but not constant linear. Number 2, y equals x squared. That's a parabola just facing up, centered along the y-axis. That's going to be A right here. E to the x, just that normal exponential growth function. I can see that's F right here. It might be helpful if you draw some other curves on there too. Number 4, 1 over x squared. So remember that 1 over x It's the hyperbola in the first and third quadrants. And so if I square that, it's just going to make this other part positive. And so it's actually going to be this graph D right here. X cubed. And so there are two of these that kind of look like x cubed, h and I. But remember, x cubed is just there once. That's going to just be h. Sine of x is going to be kind of pick between b and e. The one I'm looking for sine is b. Cosine x is the e. Looking for those horizontal tangents. So cosine has a horizontal tangent at 0. Square root of x, that's going to be j. Notice it's not defined for this negative part because the values for negative x are not in the domain of square root of x. I can't take the square root of a negative number. Y equals 1, so graph G would have a graph of line y equals 1. And last but not least, number 10, tangent of x, is just going to be I. All right. Now let's do an example of a slope field where I have to, where I can't actually find the antiderivative, or maybe I could, but I don't want to. So this is a slope field, and we're just trying to match it up with a differential equation. So this is a common type of problem that you're going to see on the AP exam. So I do not want to find each of these antiderivatives because I know it has x's and y's. And so to help me out, what I can do is just kind of zoom in on the x coordinates and the y coordinates, and especially the zero slopes. So one thing I want you to pay attention to right away is if I look at a certain x coordinate, like x equals 1, if I look up and down, I see that those slopes are different. Those lines are not all parallel. So that means if I look at the y's, it's the same thing. This has to be in terms of x and y. So I automatically know any of my differential equations that are only in one variable cannot match up. So I see E says x plus 1 cubed. This is not going to be x plus 1 cubed because this differential equation has to be in terms of x and y. So when I look at these zero slopes here, those have zero slopes along the line x equals negative 1. And I also have slopes of 0 along the x-axis, so y equals 0. So I know that for my differential equation, if I plug in x equals negative 1 or y equals 0, I will have a slope of 0. That means I can, just like I would with a polynomial, if I have a 0 at x equals negative 1, the factor that's associated with that would be x plus 1. So that if I plug in x equals negative 1, I would get 0. And then if I plug in y equals 0, the factor associated with that would just be y. And so my factored form would be x plus 1 times y. So either way, if I plug in x equals negative 1 or y equals 0, I would get 0. That doesn't match up yet, but maybe we can expand. And I would see that my differential equation has to be xy plus x. That's going to be D. All right. I'm going to go ahead and make another video for that last problem. It will take us just a little bit longer, so I will see you in a moment.